Anyway, yeah. And yeah, thank you, Anna, for accepting our offer to give a talk. This is a joint seminar with IEEE Signal Processing Society Distinguished Lecture. And by the way, good morning, or depending on where you are, good afternoon or good evening. Okay, greatest honors to get our distinguished speaker, Professor Anna Scaglione, who, being some of the most distinguished in our area, may require little introduction, but I still try to very concisely. Yeah, I think I want my screen share too. I modify the slides a little bit.
You want to do, okay. So, okay.
Okay. Okay, so Anna is currently professor at Arizona State University. She got a laureate, which is the same as undergraduate degree, I think, and PhD from University of Rome, La Sapienza. She's actually fellow, actually Donald Flink Prize Award, and actually Best Paper Award, and many, many more. She is currently Deputy Editor-in-Chief of IEEE Signal Processing Transactions on Control of Network System. She was Editor-in-Chief with IEEE Signal Processing Ladders and so forth. Now, her current interest of research covers a wide spread of topics on network sciences, information processing, intelligent infrastructures, with many applications, including distributed learning, whether you talk about social networks or others, graph signal processing, smart grid, and etc. Now, before I pass it to Anna, I would like to mention this paper because while she did many exciting and impactful stuff on distributed things and graph and so forth. Okay, now this is still the word I vividly had in mind when I was a PhD student. Now, well, a lot of students these days might not have an idea, but I would like to tell you that if every one of you are doing MIMO precoding and stuff like that, now you should know that the one of the very important paper back in the 2000 is actually this paper. It significantly enriched our understanding with what does it mean by OFDM in a general sense. And of course, this paper deservingly received IEEE Signal Processing Best Paper Award. Anyway, I think we should not further delay. I would like to pass it to Anna, and let's have a warm welcome with Anna.
Thank you so much. And thank you for really the kind introduction. Let me take it from here and share my presentation. So view full screen. Oh, sorry. Let me start from the beginning. Oh, sorry. What's happening here? Doesn't seem to be easy to go backward in one shot. So you had a preview in reverse of my presentation. So my presentation is modeling and learning social influence from opinion dynamics under attack. So this is one of the many networks that I've been intrigued by, social networks. And the explanation goes through my interest in multi-agent system and cognitive agents in general. So the cognitive agent is in fact a very good model for how opinions are forged in the human decision system. Essentially, humans are like cognitive agents. They have an ability of performing actions that modify the state of the world. They observe the state of the world and measure a certain reward from these actions. And the opinion is nothing but this preference or probability or belief that an action should be taken to maximize the reward. Now, the difference between an individual that operates in isolation and an individual which is immersed in society, that obviously this individual will receive also information from its peers. And this exchange of messages in engineering a multi-agent system is typically optimized to achieve a faster and more accurate learning task. But in society, these messages are often indirect. So they occur, they don't reveal the information about the state of the world or the reward that the agent has received directly, but in many occasions are simply the observation of an action by the other peers. And so the talk objective here is to dive into the modeling of social networks and also look at some signal processing algorithm that can be devised to infer some parameters of this model. In particular, the basic questions we are going to dwell on are, the first one is how can we model swarming behavior, which is, in other words, how the other agents' actions, observations tend to lead to a certain emergent behavior in society. And particularly, we are interested, in fact, in where the learning breaks. Essentially, there are these functionalities in this information exchange that instead of leading to learning, they compromise the social discourse and lead oftentimes even to polarization in society. And so the talk is divided also in two parts, because the last question we want to address is how can we uncover who influences whom. So the first part is devoted to modeling, as I said, modeling consensus and polarization of opinions. And the second part, after we have established this model, is how to infer the parameters of this model so that one can make predictions or understand which one are the most influential agents. Once again, I have a lot of interest in multi-agent algorithm, and I stumbled on a rich literature, this idea of analyzing the dynamics of opinions through mathematical models that describe how they are forged by interactions with other agents. And the interest in applying this idea of dynamical system and mathematical modeling to opinion dynamics is very old. And in fact, it started during the French Revolution. It was a mathematician, Nicolas de Marquis de Condorcet, that started trying to apply notion of mathematical modeling and statistics, particularly the law of large numbers. And the idea at the time was to show the crowds were wiser than individuals. And, you know, the French Revolution was trying to replace monarchy with democracy. And so this mathematical argument was supporting the idea that it was a better form of government. But it wasn't until Galton, Francis Galton, published his famous paper, Vox Populi, in 1907, that those ideas appeared in a scientific journal. And so what is the basic idea of modeling learning, and why would somebody that has a signal processing background be able to read so easily all of these papers by mostly economists and social scientists? The idea is that really statistics are behind a lot of these models, or nonlinear dynamics are around all of these models. But from a statistical point of view, you can imagine that the environment or the state of the world is some latent parameter theta, and that every agent has like a sensor observation S, which is drawn from the conditional distribution of S given the state of the world. And this information allows the agent to shape a private belief, which is the posterior distribution of this parameter given the observation. And utilizing this private belief, the agents in isolation will choose the action that, if their model as rational agents maximizes their utility. But the point, as I said before, is that these actions are observed in the public square. And so the public square is sort of like a fusion center that from the actions indirectly can harness information about what the agents observed. And ideally, one will want that social learning operates really as a fusion center that achieves much more information by essentially fusing all the information from all these sensors, and therefore achieving a much more accurate answers. But in general, that cannot be guaranteed. And so, in fact, this idea of opinion dynamics has evolved. And from the times of Galton, where, as I said, most wanted to prove that statistically the answer given in democratically was better than the answer of an individual. In fact, the idea of social pressure has been analyzed and oftentimes proven to create herding phenomena or polarization, as I said. The famous experiment that Galton made to prove, however, that the crowds were wiser than an individual was he essentially asked a number of individuals to estimate the weight of an ox. So the weight of an ox will be this parameter theta, and each of them made an estimate, and he averaged them. And the sample average of the estimate came particularly close to the accurate measurement. But let's see how this kind of reasoning can lead to a model of opinion diffusion. And first, let's establish a little bit of notation and some kind of general definition. So when you have an opinion dynamical model, you essentially have some social systems equations, and they typically are either deterministic or probabilistic equations that essentially explain how a set of agents combines these private beliefs through observations that can be direct or indirect of the peer's belief. And they are indirect, for instance, when the agents only observe the actions. And once you have established this model and you see how these opinions evolve through these equations, then the goal is typically understanding what is the limiting state, which will be the emergent behavior of society. Let's denote by x sub I of 0 the initial opinion of the agent. This is formed, as I said, through what we said is the private information, like the sensor information aside, just leads to a posterior, or to an initial estimate. This will be the minimum mean square error estimate based on the observation, right? So this establishes the initial belief. This is a continuous variable. And whenever this is a scalar, if it is a probability, then you can imagine that this will be, for a binary action, the probability of selecting action 1. Each of the agents has an initial opinion, and a dynamical system that is a closed system would just simply be defined by some vector equations that, if they are in continuous time, would simply denote the rate of change of the opinion as a function of the present state. But most of the opinion dynamical models that I will describe here are in discrete time. So T is effectively the index of an epoch that represents a certain set of interactions. Now, all the social network dynamical models that I will describe rely on an underlying weighted directed graph. It's very important to think about a directed graph because social influence is not symmetric. So unfortunately, you can write perhaps a nice paper, but it would be very representative of reality if the weights were symmetric. And so we have this adjacency matrix A, whose support is equal to the edges that connect these agents. And the weights represent effectively the mutual influence that the agents have, but in relative terms. In other words, the percentage of influence that a certain particular agent is connected to another agent has. And since this is a relative influence, all of these weights add up to 1. So the rows of these adjacency matrix add up to 1. So once again, through the opinion dynamical model, we want to understand what is the steady state. And the classes of opinion dynamical models that we described justify two types of emergent behavior. The first one the first class are consensus models, where everyone eventually achieves the same answer. And obviously, in the case of Galton, the idea was everybody will achieve the correct or more accurate answer. But in fact, in more recent years, a lot of these models have been applied to justify that there is herding behavior or bandwagon effect in society. Another class of models are instead justifying the emergence of polarization or disagreement in society. And there are two types of models that we describe. One is when disagreement is caused by the fact that there are zealots with opposite views that try to lead society to splinter in multiple opinions. And the other one instead is governed by an internal mechanism that makes people stop communicating where their opinions are too divergent. So both of them lead to splintering of opinions. So as I said, in Galton's experiment, he represented the fusion center because he added up and averaged all the answers from the people he interviewed. But you can envision a simple dynamical model where all of these individuals were interrogated in a daisy chain. And if these individuals were trying to provide the most accurate answer, the dynamical model that would have led to that would essentially have done recursively a sample average. So you can see the update here. All these individuals are talking about a topic K, and let's say that this topic theta K, or the state of the world, is a sample out of a normal distribution with 0 mean and a certain variance sigma naught. And let's assume that all the private information are simply noisy versions of this state of the world theta K. And for simplicity, let's make the variance of each noise equal to 1. So the initial agent opinion is nothing but their private observation. And the dynamical system that would show that the crowd is wise, because this is the best thing that they can possibly do in order to integrate information from their peers, is to do a convex combination of their own private information with the information of the previous, with the belief or information that the previous agent passed. And this convex combination is essentially effectively doing progressively a sample mean. And so obviously this weight changes as time goes on, and the private information is weighted less and less as this information converges towards a correct value. In fact, as t goes to infinity, so for every t, this belief is a normal variable which is centered around the correct opinion and has a vanishing variance with the index t. So for a large crowd, obviously the answer becomes more and more accurate. Now, this model is very simple. In this daisy chain model, the interactions are simple, but models that emerge later to prove consensus are also very simple, but they essentially do away, in some cases, with the statistical justification for the type of dynamics. So they don't try to optimize the way to integrate information for society, but rather just study the opinions just based, as I said, with an interaction model. And the simplest interaction model possible leads obviously to linear dynamics. So here is shown in this equation, where you see that if the agents are interacting on a certain topic K with the other agents, their opinion in the next epoch, after they discuss with their peers, is a convex combination of the opinion that the agents had at time t. And obviously, as I said, these coefficients are 0 if I don't interact with some of the agents. So this is, generally speaking, not a fully connected network. I don't talk to everybody. So now this is the simplest possible dynamic. We know that if we start from an initial opinion, given that we have indicated that these weights add up to 1, the largest eigenvalue of this matrix is in fact equal to 1. And as long as the graph is strongly connected, so there exists a path from any node to every other node, possibly through several intermediaries, then the second largest eigenvalue of this adjacency matrix is actually less than 1, strictly less than 1. And this allows the network to converge to a consensus. In other words, as t goes to infinity, all of them will have the same opinion ck, and this both ways 1 is again the whole 1 vector. So consensus is reached. And the dynamics of simple linear dynamics are obviously exponential. The rate of convergence, as I said, is exactly this eigenvalue. And in graph theory, this eigenvalue is tied, is the complement to 1 of the so-called algebraic connectivity of the graph. Whenever this eigenvalue is equal to 1, or whenever the algebraic connectivity is equal to 0, then the network splits in multiple components. So obviously, information doesn't flow between different communities, and they no longer converge to a consensus. So you can see here in this graph how fast is the convergence when lambda 2 becomes closer to 0.5. The smaller is lambda 2, the faster is the convergence. A variant of this protocol is a completely randomized algorithm here. Instead of saying that everyone exchanges in synchrony all of these opinions, which clearly is trying to represent sort of an average phenomenon. The interaction are random, so I pick a random pair. In this case, I'm averaging his opinion with mine, but this could be also a complex combination. It doesn't have to have weights 0.5, they simply have to add up to 1. And in this case, the analysis is just very similar if we look at the process in expectation. In particular, in matrix form, you can see that it's as if we have a switching adjacency matrix. And what matters in this phenomenon is essentially to prove convergence and every other result is the expected adjacency matrix. And as long as this expected adjacency matrix has the second largest eigenvalue, which is strictly less than 1, which is tied to the fact that asymptotically information can flow from any point to any other point of the network, the algorithm also converges. But of course, depending on these, the frequency and the density of connectivity, or how many agents I tend to talk to, the process is faster or slower. This is reflected in the second largest eigenvalue of this matrix A, and you can see that how this randomized consensus converges in both cases. Now that we have talked about consensus as a very simple model, can we actually harness similar ideas to show polarization? In particular, in democracies right now around the world, we are witnessing opinions that tend to be divided in society. This is actually a growing phenomenon. And so this phenomenon of polarization is perhaps more interesting than the phenomenon of herding nowadays, especially to understand political movements today. So in fact, it's a simple modification of the Groot model that already can justify very simply what happens, what can happen in society that can lead to polarization. And in particular, is we can just simply model a group of the agents whose opinion here are indicated with this vector Z. Again, T is the epoch of communication and K is the topic over which they're communicating. And so these block are the opinions of what we call the zealots, while Y are the opinions of the normal nodes that are not stubborn. And in this case, we have these weighted adjacency matrix that for the zealots does not change the opinion, right? So the zealots maintain the opinion that they had originally, and they are not influenced at all by the opinion of the non-stubborn agents, while they influence through this block of the matrix, block P of the matrix, the other agents. And then obviously the normal agents also have some influence on each other, which is represented by these, the weights in the matrix D. And it's a very simple exercise to show that if the graph is strongly connected, these opinions will converge. The important observation here from the point of view understanding social systems is the final opinion of the non-stubborn agent is totally controlled by the opinion of the stubborn agent. So the initial opinions of the non-stubborn agents are totally irrelevant. And in fact, if the original agents don't agree, so the zealots are trying to pull society apart, then in general, this vector Y will also have distinct opinions. So the opinion leaders essentially can tailor their opinions to just push individuals in one direction or the other. But they can do so only through the particular structure of influence, which is represented by these two matrices. So here just is an illustration of what I just said. In this case, we have one single zealot. The result actually will be equivalent if you have multiple zealots, but they all agree. The zealot has this blue opinion, and it just pushes all society to this particular opinion. If in some cases the opinions of the stubborn agents can be diverging, in some cases the opinion of the agent settles towards the middle. In other cases, it doesn't settle towards the middle, but in both cases, you can see in the second two figures with 2 stubborn agents or 3 stubborn agents. The more diversity there exists in opinions, the broader is the spectrum of opinion that the remaining part of the society has. And it's actually important to notice that the opinion of the non-stubborn agents, if you have a set of topics that are discussed, the covariance of this opinion in general, if you have many topics that are discussed, will have a covariance which has a rank which is equal to the number of stubborn agents S. So this is an observation will be important later when we try to identify the model. Now, the very interesting fact is that you can do a minor, relatively mild modification of this model that though leads to nonlinear dynamics that showcase the splintering of opinion, which is not under the pressure of zealots or the control of any individual, but rather is due to an internal mechanism that makes people not discuss with other people that have an opinion which is too divergent. This model was introduced in 2002 by Hegelman and Krauss. And the idea is very simple. It's a simple modification of the de Groot model where the weight AAJ is now multiplied by, this is a step function, it's the Heaviside function, which becomes 0 if this parameter, which is the distance between the current opinions of agent I and agent J, exceeds a certain threshold tau. So if this distance, the opinion distance exceeds the threshold, then the influence disappears. Otherwise, it continues. And the complication in analyzing this model is, as I said, that this is an opinion, a nonlinear dynamic, because this matrix of influence now depends on the time through the state itself. In fact, you can see that there is a much funkier behavior in the trends that you observe early on as the interactions occur. Here, the difference between these graphs is that the threshold becomes lower and lower. So here is 0.25, here is 0.2. These are opinions that are between 0 and 1. These are, again, beliefs or probabilities. And you can see that as the threshold goes down, the society splinters in 2 groups and 3 groups and so on. And of course, there is a variant of this model that is similar to the randomized interaction that we discussed before. This model was introduced by Defuan, where agents wake up at random, they interact with the peer, and they average their opinion with that of the peer only if the opinion distance is close enough. And so there is a stochastic aspect in this. Now, the stochastic aspect actually in certain ways helps, because we were able with my student Linley to analyze resorting to a stochastic ODE approach. And the goal was to understand how the initial opinion, not the threshold, was, rather than the threshold, was affected this trend. Because the same exact threshold leads to different outcomes depending on the parameters of the network and the initial opinion. In fact, it depends on the initial opinion distance. And what we were able to prove is that a necessary condition for the system to converge almost surely to consensus is that the threshold is greater than the sum of the expected weight, influence weight, times the initial opinion distance. Now let's go to a different kind of model. So far, it's clear that in the interactions, the agents are exchanging their opinion, their continuous belief. This is as if the other agent is almost reading their brain. And conceivably, you can imagine that 2 agents may observe many actions from the same agents and then essentially estimate the belief, and then at that point internalize a change in their own decision system as a result of that. But in many cases, you see that social influence occurs at a much faster pace, and people just observe an action and internalize that action and change their belief or the way they approach the next action just based on that single observation. So for this type of, to capture this type of phenomenon, we have another class of models that are so-called voter models. And the voter models is concerned with actions that are binary, so yes or no, In this case, just say 1 of 0. So AI TK is the action that they take about topic K at time T. And the agents still have an initial belief. This is the probability of selecting action 1, right? And this could be also the posterior of a certain binary variable theta K that says, you know, the restaurant is good, the restaurant is bad, so I should go to the restaurant. Now, the interesting thing here is that these voter models, just because now the message is quantized, right? I don't have access directly to the belief, but I have access to this action, lead to herding. And there are two classes of models that essentially achieve the same result, but through very different routes. The first came from economics in 1992. These fellows, Bichkanani, Kirschleifer, and Welch, came up with this model that for short I'm going to refer as the BHW model, otherwise pronouncing these names repeatedly is really challenging. And the second one is the model by Clifford and Sudbury that appeared in statistical physics that was inspired by the Isaac model for spin alignment. Both models lead to herding. And so again, the difference is that here, what the agents internalize is the observation of a single action as opposed to having access to the belief. So the BHW model has a complication. It starts really from this statistical model where the environment has a state of the world theta. The agents have an observation, which is a sample from PS given theta. And these are all conditionally independent. And based on that, the agents try to optimize their own expected utility. In particular, the environment can be in good state 1 or bad state 0. And the agent have a gain if they select action 1 when the world is in a good state. And they lose if they select action 1 while the world is in a bad state. While if the action is 0 and the world is in a bad state, there is no gain and no loss. Okay, so in this case, the optimum rational agent Bayesian agent decision is to choose an action that maximizes, in fact, the posterior of the state of the world theta, given not only the private information at time t, but all the actions that have been observed previously. Now, to do this in a totally randomized interaction becomes really complicated because this posterior is really difficult to calculate. But if the interaction occurs in a sequence, so the first agent performs an action just based on the private information, then the second internalizes the action of the first and the second, and so on, it's actually possible to write this action rule in closed form. And that allows to show that, in fact, the likelihood ratio that selects the action is a martingale. And in a finite number of interactions, the agents herd and make the same decision irrespective of what is the private information that they observe. And the decision towards which they herd can be wrong or right with a certain finite probability, which means essentially that people may all buy the same stock irrespective of the information that they have. It could be very accurate that the stock is total crap, but they keep buying it because they are overwhelmed by social pressure. And what is interesting in that model, I would say, is that this herding phenomenon is under a completely rational behavior. So this agent couldn't have done any better in integrating the information that they had in terms of accuracy. Nonetheless, they can make mistakes. So they don't achieve learning. The voter model instead is more in the spirit of the de Groot model. It just establishes a dynamic. And the dynamic is very simple. It says people at random look at one of their peers and they imitate their action. Clifford and Sudbury just analyzed this idea numerically. But so it wasn't until Hawley and Liggett revisited this model that there was actually an analysis. So this idea of waking up and finding one of your peers and copying the action can be mathematically described in fact, as follows: absolutely equivalent to drawing a random variable, binary random variable, out of a Bernoulli distribution that has a probability, a parameter xitk, which is the histogram essentially of the actions of, it's just the average of the actions over the neighborhood. Okay, so that represents the new probability, and with this new probability, a new action is taken, and this proceeds. And as t goes to infinity, for finite graph or 1 and 2-dimensional lattices, all actions will almost surely converge to the same action. This action can be 0 or 1 with a certain probability. And so this actually also shows that in general, even though there is no optimality, obviously, in copying your neighbors, here herding again emerges and can lead people to choose the wrong action. Just in case people are interested, actually, this idea of herding, it can be analyzed in a very interesting fashion. The idea is to track the origin of an opinion at a certain node, going backward and viewing this opinion that travels from one agent to the other as a random walk. So each agent at a certain time t essentially can be traced back to an opinion that jumps from a neighbor to the other. And so if at some point these origins, if you go backward, converge, that means that those agents will have the same opinion. So whenever all of these random walk end up converging as you go backward, that means that you have essentially achieved the same opinion across all societies. So studying the time it takes and the probability of having random walk that coalesce amounts to essentially proving the convergence of these algorithms. And I made use of this with my student Ercan Ilditz in 2011 to look at the modification of this model where there are stubborn agents. In other words, people that want to set an example and always take the same action irrespective of what the other nodes do. Although obviously the other nodes that are non-stubborn may copy them. So in this case, if there are opposing views, if there are zealots that hold diverging opinion that keep doing one action 1 and the other one action 0, you cannot envision that there will be herding, right? Because there is always a finite probability of talking with an agent that has an opposing opinion. But what we were able to prove is that this phenomenon converges in distribution. And what is very interesting is how the variance of the opinion changes depending on the placement of the agent. So for instance, here I have an agent in this particular network in the placement 1. They are at the 2 edges of this network. You see that the variance is relatively low. When I instead place the agent here, and the variance is actually very high because it's actually, it takes longer for the intermediate agents to potentially receive again indirectly opinion through these 2 proxies. And the problem of socializing, of maximizing the social bias is actually a submodular problem. So we found a near optimum solution to that is greedy to place strategically these agents so that you can achieve the bias that you prefer and also try to capture the variance, the minimum variance that is desired. So let me go to the next part of the talk, which I will have to abbreviate a little bit because I have only 10 minutes. So let's talk about the identification of social networks. And this actually was work that I largely did in collaboration with Hoi To when he was a PhD student here at the ASU. So of course, people have tried to look at statistical models, particularly graphical models, to understand social influence. And the idea is essentially to estimate the sparsity of the precision matrix, the inverse of the covariance matrix, to infer the underlying graphical model structure that justifies sort of the Bayesian influence among agents. And a lot of the research here has not been so much on the social network side, but rather in improving various heuristics to estimate this graphical model effectively. So the prevalent heuristic utilizes so-called graphical lasso, which was introduced by Friedman et al. in 2008. And the idea is to minimize this cost, where A essentially is the precision matrix, right? It tries to estimate the inverse of this estimated matrix X, and the problem is regularized for sparsity with the lasso relaxation of using the L1 instead of the L0 norm. So there are a lot of work that again applies this graphical lasso for system identification. But as I said, most of them were concerned with improving the algorithm. And among people that do bioinformatics, there are other statistical methods that are popular: ANOVA, Tigris, Gini, and so on and so forth. And they have been applied to social data. Now, what I object is that if we will go back to the models, particularly to the model of the group model with stubborn agents, I will object that one of the problems that we have here is that societies tend to be very large. But the observations are going to have a rank which is relatively low, which is the size of the stubborn agents group. And so we have a big data problem, which typically will require high rank, right? If you are trying to estimate the inverse of a matrix that has low rank, you have to expect to run into problems. And we will see that that's exactly what happens. And this justifies the idea of, furthermore, I like to add that the precision matrix will be necessarily symmetric. So it doesn't give you an easy avenue to study a directed graph, which is what is of interest here, right? Because we know society tends to be directed. So the idea is to utilize this phenomenal polarization that happens due to the presence of opinion leaders sort of as the excitation of the system. We called it in the first time we published it as like a social radar, right? So the opinions of the zealots are like a perturbation of the system. And basically the output of this system depends on the excitation through this system equation. So having several observations will allow essentially to infer what is the underlying, to do a tomography essentially of this underlying influence network. So also in this case, we can set up our estimation by looking at a certain loss function that essentially penalizes the fit with our model. Our model can be written in terms of the several observation K in this fashion. EI is simply a coordinate vector. This comes from this identity matrix. So if we write it on a row by row basis, we can see that we have a least square cost here for the lack of fit of this equation. Then we want sparsity, so there is not a lot of there are not a lot of entries that are non-zero in this influence vector. And then we have the fact that these weights have to add up to 1. And we also have a further constraint here that each individual influence itself, in this case here we put 0, but in fact we could put any constant here. Why? Because there is an issue of identifiability here. So we can identify the relative weights in D, but we cannot identify exactly the diagonal term. So every estimate that we'll make of the parameters in D will be up to a scale. But in terms of this, if we want to identify the support or the relative weight of the agents, then it's appropriate to inquire to what extent, I mean, how many stubborn agents we will need, or what kind of signals would allow us to estimate the system. And so because of the structure of the problem, it's not only sufficient to have persistence of excitation. In other words, having sufficiently different opinions expressed by the stubborn agents. But we also need a certain particular intensity of the signal, right? That's governed by the matrix B, which translates in a certain sparsity and a certain number of such stubborn agents as well. And what we were able to prove is that for a class of random graphs, there is guaranteed identifiability as long as the number of stubborn agents that we have is in the order of the degree, essentially, of the matrix D, which is the amount of agents that influence each other among the non-stubborn agents. Now, this actually is a very mild requirement. That means that it's possible to identify the system, even if there are low rank data, because in general, what we are assuming is that we are not influenced by many peers, but only by a limited number of peers. So this number is very small compared to the requirements that you will have for graphical lasso. And this is a theorem which is fairly complicated to read, that Tog came up with, but the bottom line of this theorem essentially establishes more formally this concept that, roughly speaking, the system is identifiable if you have a number of stubborn agents that is in the order of the maximum degree of the network. Now, this condition for identifiability is under the assumption that you can place strategically, you can have a particular good structure for the influence matrix, this B matrix. But in general, we will see that it is actually a very good predictor of the phase transition that exists between identifiability and lack of identifiability, because you don't have enough agents. So the performance benchmark that I want to show are relative to the so-called IUROC performance, the area under the ROC characteristic. And another measure that we have is the area under the precision and recall ratio. And also we have the normalized mean squared error in the estimation of the weights. And what's important here to notice in this comparison is as follows. So here we have the area under the this figure, the area under the precision and recall. So we are comparing here for an Erdős-Renyi graph, is a completely random graph with n equal to 100 agents and with a probability of connectivity which is 8%. The performance of our method, our methodology, which is the one here in equation 9, and another method, which I'm sorry, I apologize, there is a question mark because I removed that equation. This method, we simply assumed that we placed optimally, right? Is the support of B is known, right? And they are all we are in the active sensing scenario. So obviously the best is the active sensing scenario, right? The matrix is symmetric in order to give the chance to graphical lasso to do a good job. And the green one is instead, we don't know the support of B, so we solve exactly that problem. Well, graphical lasso is this blue line. And this is the threshold of theorem 1, which, as you can see, is a little bit of a underestimate of what you need, in fact, to converge. In the right-hand side, we have just a bigger network. Of course, here, the sparsity, we're trying to maintain it roughly to the same level, okay? And the graphical lasso is missing because of exactly what I said, that the numerical problem becomes too difficult to solve. Okay, so let me move forward and skip a few of the data because I'm out of time. Here are the measures of the normalized mean square error. The only interesting really part here is in the case where we can actually optimize the position of the stubborn agents according to the theorem, we can see that there is a dramatic improvement in mean square error exactly at the threshold. while if we cannot optimize it, we still have relatively good performance, but we don't do as well. And then finally, here I have a few real data analysis, and this was actually a fun process that I did with CC Wu. We had the roll call votes of the US Senate for a few years, from 2015 to 2019. And in this case, the goal was obviously to identify a much polarized Senate with different groups, and Democrats and Republicans being stubborn or affecting each other. And the interesting thing is that we were able to pick up a lot of interesting facts. And in particular, we were able to, by estimating, using exactly the same algorithm, you can see that the algorithm can correctly identify and cluster Democrats and Republicans, right? So these, but the interesting part were the matrix of influence between Republicans and Democrats, and this correctly picked up senators that are known to be moderate in each camp. And if we measure the impact of the senators through how many senators are influenced by them, or just also by the sum of the weights, then we were able actually to pick up that Tim Kaine was a very influential senator. It was almost unknown before the 2016 election, and was picked by Hillary Clinton as the vice VP candidate. And other things that were interesting were, you know, all the sitting senators here were picked as having a very large network, which is also accurate. So in conclusion, there are a lot of interesting models that exist. I touched upon some of them, and even simple models like the Groot model with stubborn agents can be useful to do better than just looking with a very black box graphical model type of approach to this social data. And they lead to an interpretation of the data that is absent in many other statistical methods that are employed without explicit opinion dynamics modeling. So the one drawback of this simplified model is how do you go from the plethora of internet data, that typically Twitter data or Facebook data are through text, to extrapolate what is the individual opinion, and probably some latent semantic analysis should be done. And then from that, capture what is going on with this phenomenon. So for voting rating system or simple retweeting, like these models are directly applicable. You can get estimates like we did for the Senate data. But in general, if one wants to understand more complex opinions about topics, then the idea of characterizing what is the belief of the agent can be much more complicated. With that, I conclude, and I'm happy to take questions.
So, all right. So, so this is the Q&A session. This is the Q&A time. So, actually, we got a question from Ken. So,
Okay.
actually, do you like to ask the question yourself, or do you want me to repeat the question?
Maybe you do.
Okay. So, so Ken has a question on page 30 for this on the slides.
Okay.
So, he want to know whether we know the positions of the stubborn agents in the network identifications.
So in this particular formulation, we do not. We try to identify both D and B without knowing it. The identifiability result, though, assume that we actually do know the support, and they also make assumptions on the graph. In other words, not every graph would be able to satisfy those conditions. So they're sort of ensured that there is enough influence from the stubborn agent to the non-stubborn agent to create enough diversity.
Yeah, because
in
the way I understand the problem when you formulate it is that you have Y and Z. So in a way, we have a prior to partition. I mean, well, if my understanding is correct, you already have a prior to partition them. So that's why I had this question.
So the partition, I know who are the zealots and who are not the zealots. Later work that we did allows you to cluster them prior to doing the identification. But, you know, in this particular work, we didn't assume that. We assumed that we observe the opinions. We know who are the zealots and who are not. Like, could be the news sources or, you know, advertisers and so on and so forth. In this particular problem, you see that I haven't constrained the support of B to be known, right? So if I knew the support of B, then that would be obviously additional information. So I wouldn't need to have the L1 regularizer. I would actually force to zero the entries that I know are zero and just try to estimate the other weight. So obviously we would be in a better position. I have, just to reduce the number of slides, I actually have erased that equation. That's why we had this question mark here, because I actually had erased the equation. But that is the problem where I do know the support exactly.
So we got a second question from Zhonghui.
Okay.
So he asked, so for some agents with a tendency to be stubborn, did the result tell us what kind of topology can help to change their opinions?
You mean basically how should we change the matrix B? So B is how the stubborn agents affect the others. In the model that we have, the stubborn agents don't really have a network. They just don't.
I mean, those agents who are not exactly stubborn, but who's unlikely to change their opinions. So
unlikely means that they will be essentially, they will have a very little weight for everybody else.
Yeah, kind of.
The result says essentially that nonetheless, as long as they have epsilon weight, non-zero, they eventually will be driven. They will be driven by the opinion of the stubborn agents, right? But you can see here that if I have exactly one in the diagonal and zero everywhere else, obviously that entry will disappear and the matrix will not be invertible. So basically, if that agent does become stubborn, then you have to include it in the other vector, otherwise this equation doesn't make sense, right? So the tiny difference that you have here will be because there has to be an epsilon weight towards some other agent that is non-zero. And as long as that's true, this holds, because essentially this is invertible since this matrix is always substochastic, so the inverse exists.
Okay, so we have a third question from Lee. So actually, do you want to ask the question yourselves or not? Okay, let me do it. Okay, so he or she is asking. So a general question is that he or she appreciates your comments on. Is there like a potential information leakage in the process of evolution? Like, for example, some agents may infer private informations of other agents in some way.
Yes, I mean, the idea here is that, of course, I may have direct observation. So in these models, we have two classes, right? The ones where we have direct observation of the beliefs. Effectively, those can be only estimates, right? But that will be the case where you essentially have seen what the other agents have seen, or you have seen what they have learned, right? In the voter model type of situation, instead you only see their action. So you can infer part of the information, but not completely. You have a very coarse quantized version of the private information. And so in that case, I will define it more as a leakage. So the other agents didn't intend to tell you anything of their private information, but just by acting, they are revealing something that they know about the state of the world, or that they have experienced And that is really how information leaks through society. And I would say, if I can add, like, that I think I find very interesting that all these models where there is leakage of information rather than direct observation of this continuous information, they lead to herding. Like, everyone ends up doing things that are the same, and they may be wrong or right with a certain probability. I hope I answered the question.
Yeah. So let's wait for Lee to say whether that is the answers. Okay, sure. So let's go for the next question. Once again, that is from Ken. So he want to know, is there no way that we can stop vertical disagreements and polarization, or is there anything we scientists can do in general?
Well, yes. So when, in the case of the stubborn agents, you right, in the model where you have the social influence from the zealots, you really have to cut the ties with the zealots, essentially, right? So if you undo that communication channel, like if Twitter and Facebook were to control the stupid ideas that are posted in their sites, you probably will have less extreme opinions spreading around. In the more interesting model instead is the bounded confidence model, right? Where there are no stubborn agents, people split because at some point they don't talk to each other. And in that case, actually, instead the stubborn agents could help, because they could push, the other agents to come closer, right? And if they continue to push to come closer, then eventually they can actually lead to a consensus. Because as I said in the case, the initial opinion on average matters, right? So if you can restart the system and just push the initial opinion towards being on average below the threshold, then there is a greater chance that they eventually will collapse. So in that case, in fact, putting people that are stubborn, but that they try to reconcile the society that is splintering, can actually help. So it's kind of interesting that it's exactly the opposite.
Yeah, I guess that's also an important question for all of us. So next up we have another question from Zhonghui. So he wondered how we should model the PS given theta, the conditional probability, and also how about if the observation itself is biased in a way that, for example, when people are watching some biased media, and what is so essentially his question was about how does the
bias is it's included in. So if you have a biased information, right? Let's say that you have a simple model. You say, I observe theta in noise, but now the noise has a mean which is non-zero, right? So then you have a biased information. Now, of course, the issue is also how you process that statistical knowledge. Because if you don't know that this information that you are served is biased, then you may process it incorrectly, assuming it's not, right? But typically what the private information models is what you see, right? It's not what comes from other agents or the news, but exactly what you see with your naked eyes, okay? So if you have prior bias, that means it's part of your interaction with society before, or what you have memorized before, and that is essentially incorporated in the private information that you have about theta, right? So here you can imagine that I've saturated this distribution with respect to everything, right? That is the random state of your mind, except this new little piece of information S that you observe, that is not a message from any other person in society. It's just exactly what you see. Like, you see the price of the stock. You haven't talked to anybody, right? You haven't listened to the news, and you decide to buy or sell. And so what S is really the uncertainty on you knowing exactly that information is accurate, right? You may have an outdated measurement, or you don't trust whatever the software that is giving you those data, right? So So that is really what S represents, and it depends on the situation. So Galton was saying you have an estimate, a noisy estimate of the weight of the ox. Maybe you're not observing it well. You have an inability of, you know, with the naked eye to weight an ox, right? So, but based on your past experience, you form yourself an idea that an animal of that size should have that weight. So in many cases, like constructing these models is subject to interpretation, and whatever is convenient. It's not too far from reality, but it represents something reasonable. Or you can empirically construct them, right? So if you have the state of the world, good or bad, and you have a lot of measurements, you can sort of empirically estimate these distributions.
Okay, so next up we have a question from Mingjie Shao. So he would like to know, so what if there are more than 2 options in the network besides 0 and 1?
Yes, actually that's easy. So if you have a categorical choice, right? Then imagine that each xi is effectively a probability mass function, and you can exclude one of the entries because it obviously has to add up to 1, right? So if there were 3 options,
multi-dimensional.
Right? So we will have for each agent, you will have a little vector, which is the probability mass function.
Yeah.
Essentially.
So a follow-up question will be, what will be the definitions about consensus?
Consensus, right? So a consensus is, again, when there is consensus in belief, is that you then have the same probability mass function, right? Just like in the Bernoulli case, you have the same probability. All agents have the same probability. If you have something like a voter model, then that you all take exactly the same action. So if there were 3 actions, you will all take action 2 or 1 or 0. And collectively, there is a certain probability that the phenomenon will converge towards that particular case, but anything can happen, right? If you simulate it, you can end up in action 1, 0, or 2 with a certain probability. And actually, since on average, particularly the voter model, if you take it, the expected action looks exactly like the de Groot model, you can calculate what is the probability that society will end up in one state or the other exactly through the same equations.
So actually, he also got one further question on how do we infer the stubborn agents?
How do we, yeah, so this is more recent work that we did also with Tom, is essentially by clustering, right? So we can utilize the covariance of the opinions of the entire network, not just the non-stubborn agents like we did in this work. And as you have seen there, the matrix has this kind of block structure, right? And so looking at the covariance of this matrix, we can essentially isolate what are the communities in this graph. And the community for stubborn agents is very splintered, right? Each stubborn agent is an island. So these agents will appear to be as isolated nodes in the network. And this community estimation is using, this is a really nice idea that To came up with. You can actually prove that essentially the principal eigenvectors of the covariance are obviously the lowest eigenvectors of the precision matrix. But these precision matrix lowest eigenvector are utilized in spectral clustering to exactly identify the community, and it's simply a relaxation of an integer problem that tries to divide the graph in blocks. So that is what I will do, and I actually should include it in this talk. I think the talk is long enough as it is, but I probably should include it in this talk.
That's true. Okay, so is there any other questions from the audience? So we have cleared the batch currently, but I mean, please feel free to ask more questions, I guess. Right? I mean,
and you can also send me emails if you're interested. And so I send you the slides, so the references are at the end of the slides.
Oh, yeah, so for the audiences who are still here, so you can actually download the slides from the seminar's website, and it's available around 1 hour ago already.
Yeah, and feel free to send me emails if you have longer questions.
So I guess there are no further questions. So let me stop the recording.